For April 7th. I have this review linked on my calendar. It's 8 pages, so only print it if you really want to. Otherwise, you can kind of just treat this like a lecture, have your notes out, take notes on the features of trig you're not understanding super well yet. Try some of the practice problems. But only print it if you really want to. A lot of this is just sort of information with problems mixed in. So let's get started. The objective is to review trig, angles, trig functions, identities, which we haven't really talked about that word before, but that's any relationship in trig, sort of like a formula, but it's just like two things that are equivalent. Formulas, graphs, domain, ranges, and transformations. Starting with angle measures. So angles can be measured in two different ways, in degrees or in radians. The following picture shows the relationship between the two measurements for the most frequently used angles. Notice degrees will always have the degree symbol above their measure, whereas radians are a real number without any dimension. So the number 5 without any symbol represents an angle of 5 radians. But what I'll say about this is that radian measurements almost always have pi somewhere in their measure, because that's what connects them back to these degree measurements, makes them useful. All right, an angle is made up of an initial side, positioned on the positive x-axis, and the terminal side, where the angle lands. It's useful to note the quadrant where the terminal side falls. Why is that useful? Well, it's because of our all students take calc diagram. If I know which quadrant I'm in, I know if my trig function should be positive or negative. All right, rotation directions. Positive angles start on the positive x-axis and rotate counterclockwise. Negative angles start on the positive x-axis and rotate clockwise. So I always think about it as it's the first move you make. If you're going up, it's positive. If you're going down, it's a negative angle. All right, conversion between radians and degrees when radians are given in terms of pi. So degrees to radians. The official formula is you take the degrees and you multiply it by pi over 180 degrees. The reason this works is because this is a form of 1. All right, pi radians is equal to 180 degrees. Therefore, this just will cancel out degrees because degrees are on the bottom here. So convert 120 degrees into radians. So I take 120 and multiply it by pi over 180. All right, and then I kind of want to pull the pi off the top, put the 120 on top, and then simplify that fraction. The zeros cancel out. I've got 12 over 18. Those are both divisible by 2, so 6 over 9, divisible by 3, 2 over 3. So 2 pi over 3 radians. Or another technique is just plug 120 divided by 180 into your calculator and then hit math, enter, enter to convert it back to a fraction. So 120 divided by 180, math, enter, enter, and I get 2/3 and the pi stays on top. Now you can just leave your answer like this, or you can write rad just to like make it clear, but it's actually not 100% necessary that you write rad there. Radians are unitless. All right. Going the other direction, you just flip that over. Instead of doing pi over 180, you make it 180 over pi. So if I take some theta number of radians multiplied by this, I will get the answer in degrees. Degrees is on top now, so that's why we pick that up as our unit. Convert pi over 5 into degrees. So pi over 5 times 180 over pi. We pick up degrees. Pi cancels out. 180 divided by 5 is 36. So we get 36 degrees. And this one, you do have to write the degree there. That is a necessary part of the measure. Okay. Next page. For your reference, 1 radian equals about 57.3 degrees. This is kind of useful to remember in case you don't have pi in your radians. You can kind of approximate how many degrees and then picture it. That's how far, if you took the radius and you laid it out over the circumference, how many degrees you'd be able to cover. It's about 57 degrees. Go all the way around, you'd be a little over 6, and it'd actually be exactly 2 pi, which you can do in your head. That's a little over 6. All right. A radian is defined by the radius of the circle. I think this is what I was just saying. If you measure off the radius of the circle, then take the straight radius, curve it around the edge of the circle. The angle this marks off measures 1 radian. And that also explains why this is unitless. It is a ratio, and ratios are inherently unitless. It's the ratio of the radius to the circumference. Okay, arc length. When using radians, you can determine the arc length of the intercepted arc using this formula. Arc length equals radius times degree measure in radians. Very easy formula, S equals R theta. This is one of the reasons radians is so useful, is it makes this formula very easy. There may be times you'll use variations of this formula. Find the length that are pictured here. It's not a great image, but I think that says 5 pi over 4. Let's just say it is 5 pi over 4, which would correspond to this angle out here. With a radius of 5, so I'm just going to multiply that 5 in there, and I get 25 pi over 4, and we'll just say units. What is that actually measuring? It's measuring from right here, going on a curved path, all the way to right here. Let me just take a quick pause. All right, and we're back. Next page. So trigonometric ratios. The 6 trigonometric ratios are defined in the following ways based off a right triangle and the angle theta. Adjacent is the side opposite to angle theta. Opposite is the side opposite to angle theta, and the hypotenuse is the hypotenuse of the right triangle. Pretty obvious. The two that you might mix up are adjacent and hypotenuse because they're both technically adjacent. Hypotenuse always the longest one, always opposite that right angle. All right. So if you know this angle, then just, and this is a right angle, because of the triangle sum postulate, you will know this one as well. We'll just label it, we need a different Greek letter, we'll do an omega. An angle is our indication for similarity of triangles. And so because we know 3 angles, the ratios of these side lengths are fixed. All right, so if you know one of them, you know all 3. That's what the trigonometric ratios are telling you. If I know that this is a right triangle and I have another angle, and I know one side length, I can figure everything else out because it forces the other side lengths to be a certain length. It's the only way to make that triangle work out. All right, and then your calculator can do these functions, sine, cosine, and tangent of an angle, and it will tell you what that ratio is. If you plug in part of that ratio, then you get the other part. So SOHCAHTOA is a good way to remember that sine is the ratio opposite of hypotenuse, cosine is adjacent of hypotenuse, tangent opposite of adjacent. So realize with normal trig, they take in angles and they give you ratios of side lengths. You have to plug in an angle. And whether your calculator is in degree mode or radian mode tells it what kind of angle to expect. And then it's going to give you the ratio of the requested side length. If I say sine, I want the ratio of the opposite over hypotenuse of a right triangle with that angle. All right, and there's all of them right here if you want to copy them down. Notice cosecant is sine flipped upside down, secant is cosine flipped upside down, and cotangent is tangent flipped upside down. And this right here is backwards of what I think it should be, and I just remember that. And that's how I remember that cosecant goes with sine, secant goes with cosine. And then this one makes sense, tangent and cotangent. Why can't, I mean, they should just call this cosine, cosine, but no, that would be too obvious. All right. Find the exact value of all 6 trigonometric functions of the angle theta shown below in this figure. So we have to assume this is a right angle. Nothing will work if that's not a right angle. And we need to find this length down here. So off to the side, I'm going to use the Pythagorean theorem to find that length. 5 squared plus b squared equals 13 squared. 25 plus b squared equals 169. Take away 25, take away 25. B squared equals 144. Square root, b equals 12. This is actually a very common perfect right triangle, or at least right triangle with integer side lengths. It's called a Pythagorean triplet, 5, 12, 13. A good one just to remember. The other one that you really should remember is just 3, 4, 5. Makes a right triangle. Anyway, so let's label the side lengths with regards to this theta. This 5 over here is the opposite. 13 is the hypotenuse. It's the longest side and it's opposite the right angle. And the 12 is our adjacent. So sine of that angle theta equals 5 over 13. Cosine of that angle theta equals 12 over 13. And tangent of that angle theta equals 5 over 12. Now I'll flip them upside down. Cosecant of theta equals, I'm just going to look right here, 13 over 5. Secant of theta equals, I look right here, 13 over 12. And cotangent of theta equals 12 over 5. All right, so what is theta? Well, we could pick any single one of these to reverse. I could pick this one here, sine of theta equals 5 over 13, and I can do the function inverse sine of both sides. This is a function on your calculator, so I'm going to do second sine of 5 over 13, and it gives me an answer. I check what mode I'm in radian. I want to do it in degree. I'm going to do that again, second sine of 5 over 13, and I get 22 degrees. 22.6 degrees. Okay. Special triangles. The following triangles will help you to memorize the trig functions of these special angles. 30, 60, and 45, except for the 30 and the 60 is just the same triangle turned in a different orientation. How I remember this is that the 1 is always opposite of the 30. Also, I draw this triangle a little bit more narrow. I don't really believe that that's 30 degrees right there. I draw it a little more narrow so I can clearly see that the shortest side is going to be the shortest length 1. And then I remember that the square root of 3 is about 1.7. So where would the 1.7 go? Well, it'd have to go on this middle side length so that the 2 can go over here. And that helps me to draw out my special triangle here. 45, 45, 90, root 2, and 2. I just remember the Pythagorean theorem for why this one works. Because it would cancel these out, just make it 2 plus 2 equals 2 squared, or 4. For some reason, I don't seem to struggle to remember this one as much as this one. This one I have to really think, okay, opposite of the 30, I put my 1, and where's my 2 going to go? And then there's one more special triangle. There's the Mr. Olson's patented 90, 90, 0, which is a flat triangle with side lengths 1, 1, and 0. 90, 90, and 0 degrees. And this helps us find the trig functions at 0, 90, 180, 270, and 360. Or at least helps them make sense. All right. If the triangles are not your preferred way of memorizing exact trig ratios, then use this table. But I always just get this table from those special triangles. This looks way harder to memorize. It does have cosecant, secant, cotangent, but those, again, you get those from the special triangles. You just pick the inverse or the reciprocal ratio of sine, cosine, tangent. Okay, But even better is the unit circle. And if you draw your unit circle on a coordinate plane, and then you write the ordered pair where each of these angles intersects the circle, then part of that ordered pair gives you the different trig ratios. This requires that you have this whole thing written out. But then you can just look at it to figure out sine, cosine, tangent, whatever. These are kind of useful to remember. Sine, I don't know why they're using t here, that really should be a theta. Sine of theta equals y, cosine of theta equals the x value. So this is how I would do it. If I wanted to find cosine of 30 degrees, I would just look at the x value here. Cosine of 30 degrees is square root of 3 over 2. Sine of 30 degrees is 1/2. So it's just already written out there. To find tangent, you got to do y over x. And then secant, cotangent, you just flip them all upside down. And then this tells you where those vertical asymptotes would be, where this is going to be undefined, because you're divided by 0. But I don't know. Your trig teacher might really like that. I just think about my special triangles, draw a picture each time, and I can find trig ratios pretty quickly that way. I think it's a waste of time to try to memorize the unit circle. Just be able to like recreate the unit circle, and you're good. Okay, let's talk about domain and period of sine and cosine. Consider the trigonometric ratios as functions where the input values of t come from the values angles on the unit circle. Then you can say the domain of these functions would be all real numbers. Domain of sine and cosine, all real numbers. Does that make sense? What is that saying there? Where the input value comes from angles, then you say the domain would be all real numbers. I mean, this is true. The domain of sine and cosine is all real numbers. I don't know how that's like justifying it. Let's read on. Based on the way the domain values can start to cycle back over the same points to produce the same output over and over again, the range is said to be periodic. But still, the largest value that sine and cosine output on the unit circle is the value of 1. The lowest value of output is -1, therefore the range of sine and cosine. And they use bracket notation here is the interval from -1 to 1, including those endpoints. I like inequalities. I say -1 is less than or equal to y is less than or equal to 1. This also reminds us that range deals with y values. And when I say domain is all real numbers, I like to write x equals all real numbers. That reminds us that domain deals with x values. Okay. Since the real line can wrap around the unit circle an infinite number of times, we can extend the domain outside the interval from 0 to 2 pi. As the line wraps around further, certain points will overlap on the same xy coordinates on the unit circle. Specifically for the function sine and cosine, for any value sine t and cosine t, if we add 2 pi to t, we end up at the same xy point on the unit circle. So what this is saying is that we're retracing that same arc every single time. So we start with this interval, 0 to 2 pi. That gives us one full cycle. If we add multiples of 2 pi, we get the same values over and over. What the word for this is these are coterminal. And what I've said before is coterminal angles have the same trig values. So this is, a good description of coterminals. If we add multiples of 2 pi, so that's what the n there is doing. It's like any number of 2 pi to t, we get back to the same function. And then you do have to say what n is. N is an integer. All right. These cyclic natures of sine and cosine functions make them periodic functions. All right, so we're talking about graphing a little bit here. We've evaluated sine and cosine at lots of different common ratios. We've plotted them, we get this nice wave. What you really should memorize is that sine starts at a midpoint, cosine starts at a maximum, and then I guess remember that sine goes up first, but just that those two facts there is enough to get the initial sine and cosine wave every time. One very misleading fact about the picture is the domain of the function. Remember that the functions of sine and cosine are periodic and they exist for inputs outside the interval of 0 to 2 pi. The domains of these functions, all real numbers, and these graphs continue to the left and the right in the same sinusoidal pattern. The range is -1 to 1. So all it's saying is this wave here is going to keep cycling up and down forever in both directions. So this is just one period of an infinitely long wave. Same with this one over here. All right, amplitude. When the sine cosine functions have a coefficient in front, such as the value of a in the equation y equals a sine of x or y equals a cosine of x, this causes the graph to stretch or shrink its y values. This is referred to as the amplitude. It's also referred to as a vertical stretch, but because we started with amplitude 1, the a value directly tells you the new amplitude. All right, and we can see it can get taller, it can get shorter. With a negative, it reflects over the x-axis. Amplitude is an absolute value quantity. That means we would never say we have a negative amplitude. Period. There's a coefficient within the argument in front of the x. This will change the length of the function's period. The usual cycle for sine and cosine is the interval 0 to 2 pi. And here's how that can change. Let b be a positive number. The period of a sine b of x and a cosine b of x is right here, 2 pi over b. You just take the original period and you divide it by this horizontal stretch factor of b. Notice if b is greater than 1, it's going to cause it to shrink horizontally. It's smaller than 1, it's going to stretch to a period greater than 2 pi. You need to adjust the key points of the graph when the period changes. Key points are found by dividing the period length into 4 increments. So key points, originally they are 0, pi over 2, pi, 3 pi over 2, and then 2 pi, which gets you back to the initial spot. What this is saying is that if you want to graph using the key points, divide the key points by the period, by b as well. Helps you graph. All right, sketch a graph of y equals 2 sine of 1/4 x by hand. So we need to know that the amplitude is now going to be 2, and the period equals 2 pi over b, which equals 2 pi over 1/4, but I copied out flopped that and I get 8 pi. All right, and then you can divide that into 4 increments. So here's our new sine wave. So I'm going to go from 0 to 2 pi to 4 pi to 6 pi to 8 pi. All right, because it should cycle, do one full cycle in 8 pi units, because that's our new period. And so it's going to hit key points at 2 pi, 4 pi, 6 pi. Sine wave always starts at a midpoint and then goes up. It's going to reach its maximum right here at 2 pi, hit a minimum, or hit a midpoint, minimum, midpoint. Let me connect that up. I want to show that this keeps going in both directions. And then how high up was that maximum? It was 2. How low was that minimum? It was -2. That's because of our amplitude. And that's how we can do a sketch of a trig graph by hand. Let's try another one. We have a 10 here, so I'm going to do 2 pi over 10, or pi over 5. is our period. All right, so another graph. We need to complete a full cycle by pi over 5. Cosine starts at a maximum, but watch out, we've got a vertical flip here. So we're actually going to start at a minimum. It's like we were at the maximum, then we got flipped down here. And then we need to complete a full cycle by the time we get over to pi over 5. So I need to go up, hit a maximum, come back down, hit a minimum, and then I'm going to show that this keeps going like that and like that. This graph's going from 8 to -8, and then let's add in a few more key points. So it hit its maximum halfway here, that would be pi over 10, and it hit midpoints at, let's see, I guess pi over 20 would be halfway to pi over 10, and then 3 pi over 20, because this would be pi over 20, 2 pi over 20, 3 pi over 20, 4 pi over 20, which would then simplify to be that. Don't worry too much about labeling those x values. I haven't talked about that very much. And you can do a pretty good sketch without even adding those in, or just adding little tick marks. All right, translations or phase shifts. So for the equation a sine b of x plus c, or with a cosine, you can determine the phase shift in a similar way. And they're given, okay, 2 pi over b minus c. That sets up the interval, but I always just say, well, I don't call it c, I call it h. And I always do h over b. Gives me phase shift. But here they've got c, so we'll do c over b. One way I remember this formula is that it's similar to this one, which was 2 pi over b. So b is always on the bottom. If I'm finding period, I do 2 pi over b. If I'm finding phase shift, I do c over b. All right. But they talk about this more complicated formula to find one interval of a cycle. I don't really care about the interval of a full cycle. I just want to know how far I've been phase shift, and then I can get my new graph. All right, sketch the function y equals 0.25 cosine of x plus, I think that's a pi over 4. We'll say it's a pi over 4. So no period change, but there is a phase shift here. And we're going to do c over b to figure it out. Well, b is just 1. And so c over b would be negative pi over 4. One thing I didn't mention is that in the formula, it's always bx minus h, but now we're using c, so it's bx minus c. So always flip the sign here. This just tells us left pi over 4 units. All right, so can we sketch this knowing that we need to move everything left pi over 4? So I'll do a quick sketch of just a cosine wave. So without a period shift, it's going to do a full cycle every 2 pi. So it's going to come down, hit a minimum, come back up, hit a maximum, with key points at pi over 2, pi, 3 pi over 2. But now everything is going to be moved left pi over 4. Well, that's half of one of these units. So everything is going to be moved this far, just a half of a unit. All right, so let's see if we can do our new sketch with everything moved half of a key point over. So I guess one way to think about it. All right, so our maximum was at 0, but now it's going to be over here at negative pi over 4. All right, we hit a midpoint at pi over 2, but now it moved over to just pi over 4. I still want to keep that pi over 2 label. The minimum was at pi, so it was right over here, but it got moved over to 3 pi over 4. Then this was 3 pi over 2. Hit minimum right there. This was, say, 2 pi is out here, meaning we hit our maximum pi over 4 units before we reach that. And so here's our sketch. Let's show it keeps going. And then we haven't labeled the amplitude yet. This is going from 0.25 down to negative 0.25. All right. I think this is our last one. Last one. So we don't have an explanation of this last shift, but it's a very easy one to learn. Any constant outside of the trig function just causes a vertical shift. So this 4 here, I'm going to move it to the end and write this as negative 3 sine of 2x minus pi over 6 plus 4, and this is now vertical shift. Okay, can we sketch this? Well, we need the amplitude is negative 3, but really the amplitude is 3, and this negative is causing a vertical flip. When you vertically flip a sine wave, it doesn't change your starting point. It just means you go down first instead of up first, so that you hit a minimum instead of a maximum first. All right, let's find our period. Period is 2 pi over b. B here is a 2, so the period is pi. Let's find the shift. Is c over b, so it's pi over 6 over 2. Notice I didn't bring the negative with. I always flip for that, what I call h value. Copy that flop, and this becomes pi over 12. And I'm going to specifically say that's to the right. And we got a vertical shift. We'll say it's up 4. Anything else we need here? Okay, let's see if we can put this all together into a sketch. So normally our sine wave would go up, but the vertical flip means it's going to go down first. Here's what a sine wave normally looks like. It completes a full cycle by 2 pi. I'll just leave it like that. Now we need the period to be just every pi. So let's just do that period shift first. So I've already done the vertical shift or the vertical flip. So now we're completing a period every pi, meaning we hit key points at pi over 2. This is 3 pi over 4. This is pi over 4. And then everything has been shifted to the right, pi over 12. So that's, if the key points are now at pi over 4, that's a third of a key point to the right. I think we can graph this now. It's not going to look amazing. But I want to keep my key points at 0, pi over 4, pi over 2, 3 pi over 4, and pi. And then I want to move everything, all of these features, to the right a third of a key point. So right about there. We did hit a minimum here. Now we're going to hit that minimum a third of a unit here, third of a unit, third of a unit, third of a unit. All right, and now we're just going to connect it up. Arrows to show it keeps going. Label our maximum and minimum. It was an amplitude of 3. So we'll put a 3 up here and a 3 down there. And that is a sketch of our sine wave. All right, call that good for this review. Hopefully you got something out of it. Have a good rest of your day.